I'm quite happy today to present or to lead this colloquium with today's presenter, Julio, who will talk about um, a package for geoscientific or spatial analysis in the Julia programming language. If you have any questions, don't hesitate to ask them. We will have a Q&A session afterwards. And with this, I directly hand over to you. You can share the screen and start with your presentation.
Thank you, Martin. Thank you. Let me share the screen. So you should probably see the deck of slides already, right? So please let me know if it's not showing up. So today, as Martin mentioned, like I would like to share with you some of these packages and technology that we're building around the Julia language for geospatial modeling, geostatistical analysis. The main one being the GeoStats.jl package, which is the title of this presentation, which is a project that I think I started around 2015 or 2014 while I was doing my PhD in geostatistics, right? So this package is actually an umbrella package that we will see in the following slides, but it's a project that is made of several sub-packages, each of which does some specific part of the geospatial modeling stack, right? So you see geometric processing, the statistical modeling bit is also in a separate package. So you see some of these packages during this presentation. And I think what I want to emphasize here is that it's all open source, of course, like the idea of these presentations and with institutes and academic centers that do research in GIS is that like we want to get more contributors, we want to get these packages more and more evolved over time. So I want to emphasize here that this full stack is open source and fully written in Julia. I'm currently the CEO at this Arpeggio Technologies company. I founded this company last year to develop this geospatial technology to the industry, right? So basically, we have some verticals of agriculture, mining, energy. We develop geospatial software for the industry. And you can find more information about myself on my personal website. So if you go to juliohm@github.io, you can find more information about my trajectory and how I came up with this software and career, if you may say. So what's the agenda of our talk today? I think I would like to come back to these two questions that I shared in the very beginning when I started like recording some of these tutorials and let's say material around the GeoStats project, which is first, I think the language Julia is not well known maybe in some areas, right? So it's always important to address this first question: why the Julia language? Why not other languages that are super popular, Python, R, or any other language that's out there? Why Julia? I think that's still like a question that's valid to raise here. And the second question is the one that's really about geospatial modeling. What's GeoStats.jl, which is this package, project, framework, depending on the context we are, like what exactly GeoStats.jl is, right? And I want to make this a bit of a live demo, right? So I'll be sharing the slides, but I also switch to like some coding bits. So you see, or at least feel a bit of the language and know why we adopted it. So Julia, why not Python or R, right? So I think there are many criteria you can use to choose the technology, right? So for Julia, there are specific contexts, like why the language was created. So some of you may already know this story, and some of you may never heard of Julia. So just come back to this point and recall what I call here the workflow of the 90s, right? So when you're working with software development, we usually, like at least people who develop code for a long time, like they know this path here, which is basically what happened when we mix a low-level language like C++ or Fortran or C for high performance with a high-level language such as Python or R for prototyping, right? This workflow is a workflow that I did a lot in the past. Before I started using Julia, I used this combination of Python and C++ all the time to get the performance I needed and to be able to do my research very quickly. And the workflows goes as follows, right? So you start with Python or R or any language that's high level and allows you to quickly come up with a solution for your toy example. Say you have a small data set or you have some crop that's of a big image that you're just analyzing locally, and you can just explore ideas quickly with a high level language. You then start increasing the problem size to see how that solution you coded up scales, right? So you see that after some point you start to struggle with the low performance because of the barriers of the language itself. You then realize that you have to rewrite portions of the code in some vectorized form. Say you start calling NumPy or annotating your code with Numba or any technology that's used to overcome some of the language barriers, like the language limitations, right? Then you get to this point which is more, let's say, peculiar to, let's say, GIS, I would say, which is you add a new feature that you realize it cannot be vectorized. For example, in geospatial software, you usually do a lot of things like searching neighborhoods and looking for the vicinity of a given location. And sometimes when you do these algorithms that look up neighborhoods and do these things, they are very hard to vectorize. So it's let's say very counterintuitive to write an algorithm in terms of these concepts that's also vectorized. And you start to realize that some of the code that you've written so far cannot scale as a whole because there are components or features that need to be written in a more low level language. And then you realize that at the end of the day, you have to rewrite the whole thing to become a production code. For example, even if you are in coming out of research and academic endeavors, you can switch to a more industrial setting and you realize that data sets are ginormous. You have more data to process and you cannot escape from rewriting the solution in a more low level language such as C, Fortran, right? So this is what used to be the workflow I had many times in projects. I started quickly prototyping Python or R and then switching to C++ in my case. And then this what the Julia community called a long time ago. So it's been there for a while. So some of you may have heard of this term, the two language problem, which is you have high level languages such as Python, R, MATLAB that allows you to quickly prototype solutions. And they work really well if the heavy computation is deferred to some low level language such as C or Fortran. Or for example, if you start calling NumPy, which is written in a low level language, right? But they fail miserably if the algorithm is not, let's say, vectorizable, right? So if you have an algorithm that's heavily based on concepts that cannot be easily vectorized, you get this bottleneck in your whole solution because you cannot get more speed when you need, right? On the other hand, you have low-level languages such as C, C++, and Fortran, and they're great for high-performance software. You can really go down to the bits and do anything you want basically with these languages, right? But they're terrible for generics, like meaning if you want to abstract some of the concepts away and program and do your coding in a more high level abstraction level, you really struggle because these languages are not necessarily the more ergonomic to write these kinds of generic algorithms, right? So I always give this example in C++ because the one that I programmed a lot in the past, and it's something that I have as a reference, right? So template metaprogramming in C++ is one way of achieving generics. It's a nightmare. Like it's super difficult to come up with very generic code with this kind of approach to coding, and so you usually slow down your productivity by a lot. So you waste days and days just fighting with the compiler to get the behavior you want, because that's how the features were organized around the language. So the Julia language, it came out with this primary focus on scientific computing and with this main goal of addressing the two language problem, right? So they wanted a language that was as easy to write as Python, that you could write code that looks like Python code, but it actually performs as if it was Fortran, C, C++ code, right? So there's the official website for those of you who never checked, like it's a good opportunity to check. It's julialang.org, and you have lots of documentation and material to learn more about the language as you go. And if you want to, if you decide to learn another language for your research or for your work. here I'm giving this example that I will illustrate with code very quickly here, which is the sum implementation in various languages. So if you take a simple implementation of a function, I know it's not representative of a fully complete pipeline for geospatial analysis, but think of this simple example as something that's easy to write in different languages, right? So think you want to implement the sum function that takes a set of numbers and returns the sum. If you write this function in different languages, as I'm showing here, you see that the difference in runtime is huge, right? So if you write with Julia, you get this 2.93 milliseconds, whereas if the function was written in Python, or even the built-in Python function for summing numbers, you get this huge difference where the speed up you get with Julia, for example, would be 200x compared to this lowest here, which is Python, right? So in order to show what exactly is happening here, I will just switch very quickly to VS Code, which is the one that I have here. Sorry, this one, to show more or less what's the look of these functions for people who never seen Julia before and want to compare how it would be to rewrite some code in this language, right? So in this script, I hope the letter is, the font is big enough. I'm creating a vector of numbers, random numbers, 10 to the 7 such numbers in this vector of numbers, and I'm summing with this Julia function, and it gives this expected result of 5, 10 to the 6, which is a random numbers between 0 and 1. So half of them will be 0, half of them will be 1, let's say, or anything in between. But on average, you get 5, 10 to the 6. And here I'm going to show how we would implement this sum in different languages. So you recall what you already do when you compare with the Julia code, right? So here, for example, in Julia, that's also something that you can keep in mind, is like if you need to port code from other languages that you already use, for example, if you have already a lot of code written in Python, you can call this code directly from Julia using these packages such as PyCall or Python call. There are two alternative packages to calling Python code directly from Julia. And the idea is that, for example, you can wrap the Python code into a string and prefix this string with the py prefix, and it becomes like callable Python code, right? So here I'm calling the PySum function defined in Python, saving it into a Julia variable, and then I'm also calling the Python built-in function sum here into another variable. So now I can, for example, call the PySum function that was written in Python here in Julia with the vector x, and check that indeed it's approximately equal to the sum provided by Julia, right? The same for the built-in sum. You can do the same, the two functions here, and you see that both results match. And you can also call the sum from NumPy, which is the one that's, say, written in a low-level language, right? So I'm importing the NumPy module and calling the sum, saving in a Julia function here, NumPy sum, and checking that the result also matches the built-in Julia function for the sum. Similarly, if you are used to R, you can use the rcall package to write, let's say, to reuse R code directly from Julia, right? So I'm creating this R function that sums the vector x, returns the sum, and I'm prefixing this string with the R prefix and gives me this R sum function in Julia now, right? So here is a function that I can just call. So if I go here to the terminal and say R sum of a vector of 1, 2, 3, it should call the result and return the R object, which with the value 6, right? You can do the same for Julia now, which would be like, so if you're a Julia user, you would write the function directly, right? So this is to get a feeling of how the language looks like. And if you feel that it looks pretty much like MATLAB or Python, it's pretty similar, right? So you write your accumulator on the top, you loop over the collection, you add up the value and return. In Julia, the return is optional. You can explicitly write return, but the last statement is always returned from the function. This is because we like to write in math notation, right? So if you define f of x equals 2x, it will work without having to explicitly say return to x. It's also working here, but because Julia allows you to define functions in one line like this, it's usually not seen, like the return is usually not typed at the end of the function. It's a matter of code style, right? So here I'm writing a sum in Julia, so I'm an end user of the language. I'm writing my own sum function as if I was writing in Python or in R. And here I'm taking the built-in Julia function sum and saving in another variable. And here's the third version of the function that I'm writing myself. And the only difference between this one and this one that I wrote here at the top is that I'm prefixing the for loop with this SIND instruction, which is single instruction multiple data, which is a macro in Julia that takes this code and let's say indicates to the compiler that this can be parallelized with SIND instructions, right? So this is just a third version of the sum function that I'm writing here. I can test that the result of these functions of sum that I defined match the built-in function, right, as before. And for the final comparison, I will write C code here directly. So Julia allows you to code C code directly as well. So if you have a large code base of high performance C GIS software written in C or Fortran or languages that are more low level, you can actually call them directly here. So here, what I would do, I'll create a library on the fly, right? So I create a header file from C, define my C sum function that returns the sum as if it was written in C. And this code here, I'll just compile with the GCC compiler, right? So I'll just say open this file and compile with these flags. I'm optimizing in level 3, and then I'm generating this code on this C library file, which is a temporary file that I create on this script. And then I compile the same code with the fastmath macro activated, right? So I say compile the same code with GCC, but activate the fastmath, which provides additional optimizations for the sum. So now that I created these two C libraries, I can just access the C libraries directly with the C call function. This is something from Julia as well. So I can say, get the C sum function from the C library that I've just compiled, and then save this as a Julia function, right? So this is just providing the types of the inputs and outputs to convert this into a C Julia function. And here's the version of the fastmath flag activator, right? So I'm calling the C sum function from the C library I have compiled and saving into a Julia function. And then I can call the C function directly from the library in a Julia session, right? That's also very convenient. And just showing here to illustrate what you can actually do to migrate code from Julia if you want, right? If you have this interest, you can do that. Here, what I'm going to do, I'll place all these implementations into a vector of functions, save them into these implementations. I'll give labels so that you can see which function is which, right? And then I will benchmark, which is a package that I use, and plot the result of calling this with this vector of 10 to the 7 entries, right? So I call this multiple times and record the amount of time that was taken to generate this benchmark. And if I plot here this bar plot, this Unicode plot, you'll see that you reproduce that slide I share where Julia with the SIND instructions is the fastest, right? Followed by Julia built-in, which is what the sum function that comes with Julia that was implemented by the Julia developers. Then you come with NumPy, which is, I don't know if it's C, Fortran, is a low-level language, which has similar performance, Julia beating the performance of NumPy, right? Then you get C with the fastmath flag activated, which is the next fastest, then C, then Julia, then R, and Python, right? So you see that when you come to R and Python, you see that there's already a big jump in the amount of seconds that are required to just sum the numbers. I know that's a very simplistic example, but imagine that you have a very complicated GIS algorithm that depends on loops and other things that you would like to optimize. That can make a huge difference at the end of the day, right? And here, if you plot the same speed up plot, which is compared to the lowest, which is Python, you see the speed up here of 200x if you get this code that was written in Python and rewrite in Julia, right? And that can make a huge difference with large geospatial data sets. So let me go back to the deck of slides and come back to the second, say, part of this descriptive talk, right? Which is, what is GeoStats.jl? So GeoStats.jl is this project for geospatial data analysis and geostatistical modeling, right? So it's a full stack of packages written in Julia. There's nothing written in any other language. It's fully written in Julia. That gives you a lot of, say, modeling and statistical and geometric processing algorithms for handling geospatial data. There are some things that are still working, and so that's why it's always nice to share the project with new people that are developing GIS technology. It's very nice to get to know the G_GIS group. And this project has been there for a while. We have official documentation in a website. We can also share the links afterwards. We have a community forum, a community channel where people interact sometimes, asking questions, and we're always happy to support with this questions. And as I mentioned, it's a comprehensive software stack in the sense that you just load one package. In the case here, you do using GeoStats as your import, let's say in your Julia script or in your Julia session, and you get a bunch of packages imported by default, right? Which is GeoStats is the main one. There is a submodule called meshes.jl, which is responsible for geometric processing, 2D, 3D. It's the stack we developed for geometric processing. Table transforms for doing conversions or statistical conversions between different variables in your geospatial data set. So for example, principal component analysis, all this multivariate analysis transformations we can do with this package. Variography is for spatial correlation analysis, right, which is variograms, correlation functions, and this is where this module comes in. Kriging estimators is for Kriging and Gaussian simulation based on Kriging estimators. So these are a set of estimators that work with very generic types. So you can interpolate functions, you can interpolate scalars, you can interpolate any object in a Hilbert space with this package. There are other packages for point pattern analysis, geospatial clustering, and algorithms that have been developed specifically for geospatial data in this stack. Besides this main stack here, you also get visualization stacks and IO packages, right? So there are two visualization stacks that we developed. One is with a project called Maki.jl, which is a 3D interactive visualization stack on the GPU. So you can do interaction in 3D. I'll show some of that in a few seconds. And there's another stack, which is GeoStats plots, which if you load this package, you load the stack for plotting with the plots.jl package, right? So it's a package that's more static, but has many backends that allow you to save your figures for a LaTeX article or for professional looks with different backends. There are many backends for plotting in this package here, and you can switch very easily between these backends and get different kinds of plots depending on where you go. There are packages such as geotables.jl, which allow you to load and save different geospatial formats such as shapefiles, GeoJSON. All these formats can be loaded with a single command here, geotables.load or geotables.save. It recognizes the type of the file and calls different packages to perform this I/O. And then there's other packages that are more specific to some verticals. So drill holes is for loading geospatial data from the mining industry, basically. So this is a package that saves and writes and loads files from this standard. So it's something more specific. I don't think it's very useful for other communities, right? But so you get this stack by loading the single package, and you, as I mentioned, you get a lot of functionality by default. So you get this geometric processing for meshes, you get lots of very sophisticated statistical modeling algorithms in the stack, and this 2D and 3D visualization as well. So where it has been used, so this package has been used both by consulting groups, smaller companies, and companies that we do projects with. So they are being used to write custom solutions to partners in the industry, right? So you have people using it directly as researchers inside of these companies, or people using it indirectly because we build solutions on top of the open source stack. So they are using it without knowing they are using it, but there are lots of open source that we are using to write the solutions in the company. And we have many, say, scientific publications coming out from groups in the world working on all kinds of problems. So this is one that I find very interesting all the time. I find a new paper coming out that uses our stack. I really enjoy learning something new. So this here is a set of authors working on the Hawaiian Islands. They wanted to compute these rugosity maps as a measure of complexity around the islands. And they needed to estimate these correlation functions on these images. They used the stack to perform this efficiently because we have this parallel algorithm that's implemented in the stack to compute these variograms very efficiently. There are packages, there are papers such as these ones that use it for all kinds of things. They're not just 2D maps, but say 3D material structure. So building synthetic material structure or studying properties of material structure, or even more statistical papers that just investigate different transformations on geospatial data, such as this one here, evaluating Gaussian transformations. I think I can switch to demo examples here so that you understand what exactly this code looks like, right? So if you look at this short script here, it's an example of how we would, for example, interpolate measurements from, say, stations with measurements that are just at point locations, right? So if you load the GeoStats package as you're at the top of the script, you can then load specific packages for visualization. So in this case, I'm loading the plots stack, which is one possible way of plotting the results. And I'm creating here a simple table with two columns. There are many ways of representing tables in Julia. Here is just what we call a named tuple of vectors. So I'm creating a tuple where I have a variable called z with 3 measurements and a variable called w with 3 measurements, which in this case are a string. At each of these measurements, I want to associate, let's say, a coordinate, right? So I'm just saying here, very simplistic, that these coordinates are these numbers here to the coordinates. And then there's this function in the GeoStats documentation that allows you to combine various types of tables with various types of domains. In this case, here's just a list of coordinates, but there are many more complicated domains that you can plug here and georeference your table to your domain to get a geospatial data set, as we call, right? Given the geospatial data set and a domain where you want to perform, for example, interpolation, in this case, I'm interpolating on a Cartesian grid with some 100 by 100 cells. I define my estimation problem, which takes the samples, the domain, and the variable that I want to estimate and saves into this problem. I define one of the geostatistical solvers that is also documented in the project and perform some, specify some of the parameters for the variable. So I want to interpolate Z with this variogram here, which is a Gaussian variogram with given range. And I solve the problem with the solver to get the solution. And the solution object can be plotted directly with this package, right? So if I load here this in my terminal, I can just include demo 1. You see that it created this 2 maps, right? One map here, which is the interpolated results. So I had a measurement of 0, 1, and 1, right, in this 3 circles, and it interpolated in the grid of 100 by 100 cells, the other variables in between, right? Here it also produced this conditional variance map, right, from the Kriging estimation. So it gives you 0 0 at the locations where you have measurements, and you get higher and higher variance as you move away from the measurement. That's the well-known result from Kriging, right? If you load here this second example, so the second demo here is a more sophisticated. So here I'm going to perform simulation, so Gaussian simulation over the sphere. So say I want the GeoStats package again loaded in my session, and now I will load the 3D visualization stack, which is the stack built with this Maki project. And here I'm creating, for example, a sphere, a unit sphere centered at the origin with radius 1. I'm discretizing this sphere into a mesh of triangles with this function, getting this domain. And then I'm creating now, instead of an estimation problem, I will create a simulation problem. And the simulation problem here takes the domain, in this case, the discretized sphere, and asks to create maps of a variable called z, which of type float64. And I want 500 such maps of the variable z, right? And in order to simulate this variable z, we have many types of solvers. I will use this guy here, which is called the SPD Gaussian solver, which is one way of simulating Gaussian processes over the sphere. And then you solve the problem as before, and you get this ensemble of realizations, right? So what it means is that you have 500 maps of this property Z over the sphere that you can plot with these commands here. So I'm creating a figure, and I'm plotting in the first figure the result of the first realization, the second realization, and the third realization as the color over the sphere. And if you see the result here, so let me run the demo too. It's going to generate the 500 realizations and plot here the three spheres, right? So here's one of these 500 maps. So I'm just showing the three first, but there are 500, right? So this is one Gaussian map over the sphere. This is another one, and this is another one that you can associate with the sphere. So notice that in this case, I'm associating each measurement to a triangle because I've discretized the sphere into a triangle mesh. But you can also associate the measurements to the vertices themselves. So the color, if you plot, let me actually do this on the terminal here. If you take your sphere here, which is this simple mesh, right? You see that it has 5,000 triangles, as it's showing here. You can visualize this sphere without color, which is calling this function here, and it gets just like the sphere. You can associate to each triangle a color, so you do this with the number of elements of the sphere, right? So you can color the sphere, each triangle of the sphere with a given color. That's becoming like a visualization that's more discrete, as you see, like, or you can also associate to each vertices of the mesh a color. So now it's more smooth, right? Because the visualization itself is performing an interpolation so that the colors become smoothed out, right? So it's a difference between the types of plots you can generate. And here in the third example, I would just show how you can do this over more complicated domains. So imagine that you have the mesh of the topography of some region or a volcano or some mesh that's very complicated that represents a more complicated domain. Here I'm loading the mesh of this Beethoven statue. So I'm loading the GeoStats package, loading the visualization stack again. And here's just an IO function to read a mesh format from disk, which is called dplyr format, and converting it into a simple mesh from the GeoStats stack, right? So if I call this function on this file on disk, I get this domain. And what I'm doing here, I'm just refining this domain with triangles and refining this domain with quadrangles. So I get three types of domains that I'm going to visualize so that you see that all these algorithms that I'm showing here, they actually work with very complicated domains. So if I load the demo tree, you'll see here that you get this Beethoven mesh, right? So here is one domain where you could perform interpolation, simulation with the package. So it's made of this triangles, right? So this is one place where you could assign estimates or simulate properties over with the stack we have. Here we are refining this mesh with triangles, right? So each triangle becomes a set of three other triangles, right? So if you take this triangle here, you see it was split into three sub-triangles. And here I'm refining the mesh into quadrangles, right? So if I zoom in any of these triangles here, you see that each triangle became three quadrangles, right? Which is connecting with the half edge of halfway the edge of the original triangle, right? So you have these three quadrangles, and you can keep doing all kinds of geometric processing to refine your domain or smooth it out before you start your interpolation or simulation, right? So if I take, for example, this, I think it's called domain one, right? I call it here, so it has 5,030 elements, in this case, triangles. I can do the same thing as I did before, and I can color it with, say, let me go hide here. I can do 1 to n elements of this domain, and you see that it can color each of these triangles differently, right? So depending on the property you place on top of this domain, it can come from a table or it can come from a simulation or interpolation problem. You can easily visualize with the stack we are building here as well. So coming back to the deck of slides, that's the live demo that I've just shown, right? So that's example so that you get an idea of what is currently possible with the software. And I think to wrap up, I know I have 2 more minutes, right? How to get involved? I think one of the nicest ways you could get involved is by reading the official documentation. We have the official documentation that you can find in the GeoStats.jl repository. So if you go to GitHub or you search GitHub GeoStats.jl on Google, you'll find the GitHub page probably, and there you'll find the documentation. So let me try to actually show this here. Actually, I think I will be able to. I won't be able to do this because I'm in the presentation mode, right? So you can just search for the GeoStats documentation. Is I think a first good resource to learn where things are, where the community interacts. I think it's a good step. There are the official community channel is in a Zulip instance. So Zulip is like Slack or any other chat service, but it's open source. So we adopted Zulip as our channel. If you start using it, you identify issues because, of course, we are much less mature, let's say, than other larger communities, right? So if you compare the project with other communities, you probably find issues or bugs here and there because we are smaller. So opening issues is just a nice way to contribute. And if you start to really use the project, contributing example is also a nice way to help others that are initiating with the project. If you need like further assistance, or if you have interest in actually hosting a workshop or something that's more targeted to a specific application in the group, we also give these workshops uh, at companies or research institutes. It's very nice to meet people in person, right? It makes a total difference. So spending a week or so in a group is very nice always. And we also have free video tutorials on YouTube so that you learn specific features of the project that we recorded over the years. And with that, I would like to thank you all for showing up in the presentation. I'm open for questions. Thank you.
Thank you very much, Julio. And I think that was a very nice presentation. We can give a round of applause as we would do it normally in the room as well. I think that there are a lot of questions. So the floor is yours. I will monitor the chat, but you can also just use your microphone.
Thank you, Martin.
Yes, just ask.
Yeah, there's someone with the hand raised, but it's in mute, right? I don't know if.
Yeah, can you hear me?
Yes.
Yes.
Yeah. So thank you so much, first of all. I just have one question. So how uh, flexible it is in terms of, the conflicts of environment and dependencies. So for example, these are some challenges we face in with other languages you showed. So
Nice, nice. That's an awesome question. So Julia also had this from the very beginning. Like one of the goals was to build a reproducible environment, right? So we know the pain we have in other contexts with multiple package managers like Pip, Condas. There's in Python, I know some of them because that's where I came from, basically, right? So you always have different managers, and if you mix them up, you get a headache, right? Julia came up with this built-in package manager. So if I open here, let me share the screen again so that maybe I think it's better than actually just answering you with text. If you open a Julia session, I think you can see the screen right now, right? So let me just increase. Julia has many modes. Let me put in full screen here. Has many modes in the REPL, right? So the default mode is the evaluation mode, where you just run expressions, you define a function, and you can just call the function and so on, right? But there's also other modes. So if you press right bracket, you switch to what's called the package manager mode. And this is where you manage and install packages in your environments, right? So for example, if I can press, for example, semicolon, I will switch to shell mode. I will cd into my desktop. I will create a folder for a project. Let me say full, make it full. I'll cd into the full folder. Now I'm in a folder that's empty. I'll come back to my package manager mode and I'll ask the status. You see that there's nothing there. Like I'm in my global environment actually. So it's saying here that I'm in the global environment. I'll activate my folder, activate dot. Now I'm in the full project, right? And if I type the status, you'll see it's an empty project. So let's say I start now to use geostats. So I'll just say add geostats. It will look up in the web where this package is registered. It will install all the dependencies, build everything, and keep all the versions fixed, right? So it will build a lot of dependencies. That's a huge stack, right? You see it's going to install many of these sub dependencies. And after it's done, as it's done now, you'll see that the status will return. Okay, you have in this environment the geostats version 0.39, right? The Julia language follows semantic versioning, so you can trust to some extent these version numbers if you are familiar with semantic versioning. And you can add more and more packages. So how it works is when you use the package managers like I used here, what it happens is if you exit Julia and you go to the desktop full folder, it created two files. Project Tomo, which is the file that specifies the actual dependencies you added. So I added geostats in this project. And there's a manifest file, which holds the exact version of the packages, right? So I installed one package, but it came with a bunch of dependencies, each of which has a specific version. So if you copy paste this folder in any other machine, it will be able to reproduce exactly all the versions of the dependencies in other environments. So you just copy paste the folder with these two files in it, and it will be able, any other user will just launch Julia here, activate the folder, right? So activate the folder, and anytime it runs anything inside of this folder, it will be using the versions you used as well. So I think answering your question, we have a built-in package manager that's very nice. It works really nicely compared to other languages.
Yeah, thank you. And just a follow-up question. So what would be the machine requirements? For example, looking at, so many dependencies coming all the way in the folder, does a
Mhm.
system need specific like SSD or operating? What are the operating demands or requirements?
You mean like to the binary dependencies and how it installs the binary dependencies? Is that the question?
No, just the requirement, the specification of a system. For example, I am having a system with 32 gigabytes of RAM, or does it affect the performance or?
I don't know if I got the question. You mean like if I'm installing on say Linux operating system versus Windows, if you want to check different platforms, is that the question or no?
Yeah, I mean, part of it like Windows, Linux, and then on top of that, the competency of a computer. Like for example, some programs are compatible only when you have specific size of RAM or specific size of your GPU. So does it have those requirements?
Yeah, so there are packages that are written to query hardware specifications, right? So I think one of the most famous one is HWLock. Let me see if I can find it here. HWLock, which is a project that was actually initiated by Intel, I guess. The original HWLock library, which allows you to query all kinds of things about the CPU, so the topology, the levels of cache. These are more like CPU specific. There is also, I think, CPU ID, which is a package that allows you to query this CPU information as well directly from Julia, like the vendor, the brand. There are also standard libraries that come built in with Julia. I don't remember exactly which one because usually the code you write in Julia is so portable that I rarely needed to check these things. But maybe you have requirements in your head that I'm not catching yet. But I think the C's library is the library that's it used to be called C's, I guess, in the standard library. Let me see what's the C's. Oh, it's already included, right? So C's is, I think, the built-in Julia library to check system information like total physical memory is Apple. So if I check here C's is Apple, it will return false because I'm on Linux, right? If I say C's is Linux, it will probably return true. There are some basic things built in into this C's standard library, and there are additional packages to check for additional information that's probably not in the basic standard library. I don't know if that answers your question, but I can look up more information if, or you can just send me a message with more details about the question. You can try to address later.
Thank you so much. Thank you.
Yes, please, Rodrigo. I think you raised your hand as well.
Yes, so very cool overview, Julio. I was wondering here, how are the machine learning applications like? Does this package already has some
Mhm.
built-in model? You said about PCA, but
Yeah,
if we want to build something more robust, more complex,
awesome,
let's say, like
awesome.
should we get another library, or how is that in Julia? And maybe you can comment about how's the performance.
Awesome, awesome, Rodrigo. Let me show you here. So if you go to the official documentation, like you see that there's this first let me highlight two things, right? So one thing that's very common in this machine learning stacks is to create this pipelines, right, of data transformation, which is basically you want to get your raw data sets, say your geospatial data sets over an image or over a table of point measurements or anything like that, and you want to transform into a format or distribution that's ideal for your machine learning algorithm. Say you want to perform normalization, or you want to standardize the features, or you want to do something like this. This is what we call in the pipelines here the table transform pipelines. And we have a couple of pipelines that come from this table transforms submodule that allow you to create, say, parallel pipelines for transforming data, right? So say that's the beginning of your machine learning pipeline. So if, for example, I come here to this environment that I have already loaded, right? So let me increase the font. I can do, for example, a pipeline, which is, I don't know, PCA followed by, I don't know, standard coordinates, and it will create what we call a sequential transform, which is a set of transforms that are implemented in a lazy way that you can just take your geospatial data and feed into this pipeline. So if you take your data, whatever it is, say a mesh of Beethoven as I showed, or a sphere, or a image, or a point set, or anything, it will feed to this pipeline and transform the features, transform the coordinates, and so on. That's one piece of the machine learning, let's say, workflow. And the other piece is the machine learning models, right? Which is, say, you want to train an SVM or decision tree or any of these learning models, right? So these models, they are coming from the MLJ stack, which is, let me show you here the quick start. The MLJ.jl package in Julia is the equivalent of the MLR in R. So if you are familiar with R, there is a project called MLR. MLJ is the equivalent, say, in Julia, right? So it's a framework that allows you to call all models from Python, all models from R, all models from other languages, and call them directly in Julia, right? So we have, for example, ways of finding out which models are available. I don't know if I can find this quickly here. So for example, uh, in their documentation, you can find all models that are available here from different packages. For example, this package beta ML has this classifiers, regressors, this decision tree package, which is very high performance. So coming to your point of performance, the Julia implementations of these models are usually much faster than the Python equivalent, for example, right? So we know that. But so you take a project like decision tree, it implements decision trees in Julia, right? So you can use this model through the MLJ framework by just loading the decision tree classifier or decision tree regressor. And you can plug this directly into the GeoStats framework because it allows you to do this learning process over this geospatial data set. So if I show here this example, I'm taking an example here, which is a data set from agriculture. Let me get back here. The visualization in the documentation, I need to fix this because it's not showing the colors, right? So the points are too small here, but I'm having a data set with 4 bands of a satellite and the crop type, which is a categorical variable, and I want to define a classification problem, right? So you can take this table, feed into a sequence of transforms as I showed in the table transforms pipeline, and then I can load here at the bottom what I call a classification task, which is saying I want to classify the label here is the crop type based on the 4 bands of the satellite, which are just symbols, right? So my data set has these symbols that represent variables, and I can define my learning problem. So this is a 2D learning problem where I have a source domain, which is a specific area of this agriculture here, of this farm, let's say, has labels, and another area doesn't have labels. So I create a source domain, a target domain, and my task is to classify the crop based on the bands of the satellite. And then I can load the MLJ project and load the specific model, right? So I can say, load the decision tree classifier from the package decision tree. I create this model and I wrap this model into this learning strategy here that I call pointwise learn. And you can follow the same approach we had before in the demo by solving the problem with the learner, say, and you get your geospatial data set already estimated or predicted with the integrated what we've seen so far, right? So you can plot the solutions and so on and so forth. So this is just an outdated documentation. You should have been seeing colors here. But if you run this in the terminal, you'll be able to zoom in and see that each of these pixels here has a color that was predicted versus the actual label from the data set. So summarizing, we have integration with the MLJ stack for learning with any model from other languages. So as I mentioned, you can load any model from scikit-learn, for example, because it has support for scikit-learn models. So here, if you load the scikit-learn package, you get all scikit-learn models from the scikit-learn library, for example, and you can use them directly in this geospatial data sets. And the good thing is, as I mentioned, like if you have the chance to, instead of using the one from scikit-learn, use one that's purely written in Julia, you usually get a speed up for free. So that's also something good. The code may be less tested because there's a smaller community, but it's usually orders of magnitude faster.
Cool. Thank you.
Thank you very much. Are there any more questions? So I have one question. So the popularity of Python, let's say, in the GIS environment is because of or one reason is because of the integration with GIS, like ArcGIS and QGIS. They all have Python interfaces. Are you aware of any activities going in the direction of providing interfaces to Julia directly in ArcGIS?
That's a good question, Mark. I'm not aware, but I think the people that would be able to address this question more properly would be the Julia Geo community, right? So there's let me show you here this Julia Geo community. I think I'm still sharing the screen. No, I'm still sharing.
Yeah.
So if you go to the Julia Geo organization on GitHub, that's a group of packages that are trying to interface with softwares that already exist, right? So for example, if you want to load GeoJSON file, you have the GeoJSON.jl package, which is written in Julia to load GeoJSON format, or the shapefile.jl package. These packages for I/O, or such packages such as GDAL or other packages that load existing software libraries into Julia, they are all hosted in this Julia Geo organization. And some of them we already wrap in the geotables package, right? So if you go to geotables.jl, so let me answer the question in a more organized way. So geotables is a package that uses this low-level package such as shapefile and GeoJSON and allows you to import and save data from these formats into a Julia session or into disk. Regarding interfacing with ArcGIS or QGIS or any other software like GDAL, this would be more properly addressed by the community under Julia Geo umbrella, because they're more into trying to interface Julia with existing projects that exist in other communities. Right? So I'm not aware of any initiative to write an interface for QGIS or ArcGIS specifically, but people here, they will be able to address your question more adequately.
Okay, thank you very much. So chances to ask another questions in the last minutes, if there are some. Okay, so if there are no other questions, I would say thank you again very much for your talk. I will stop the recording, so don't forget it.